I think we've gone live. So welcome everyone. My name is Sri Krishnamurthy and I'm the host of the Quant University Summer School. We've been hosting these summer school sessions for the past year or so. And today is the 46th session. I can't believe that we have done 46 lectures for the last year from eminent speakers who are academics, industry practitioners, students and postdoc researchers who've been working at universities working on various topics. And today I have the absolute pleasure of inviting Umang Bhatt, who has multiple affiliations, and I'll let Umang talk about some of the stuff he's been working on. So he's a PhD student at the University of Cambridge, and he also has a master's from Carnegie Mellon University, and we've had a couple of speakers, Anupam Datta and Julia Fanti from Carnegie Mellon University prior to today's session. And he's also going to be joining in as a fellow at Mozilla. Or have you already joined?
I've been at Mozilla since October of last year. So
perfect. So he's also a fellow at the Mozilla Foundation, and he's also a research fellow at the Partnership of AI. And I've been looking at some of the work, and whenever you look up for papers on explainability and responsible AI, you do get a lot of well-researched and well-thought-out papers. And I found Umang's paper last year, and it was kind of a workshop summary of sorts involving various industry practitioners. And I was very much intrigued, and also I'm so glad that he and this whole cohort of researchers have put together this nice paper. But recently, I came across his work again in the context of uncertainty quantification. IBM released an open source package for uncertainty quantification, and when I was reading their paper, I saw references to Umang's paper, and I read his paper, and I thought it would be a wonderful effort to kind of have him present both of the last year's work on explainability and also the uncertainty quantification. So, as some of you may know, Quant University has joined the LFAI, which is the Linux Foundation Artificial Intelligence Foundation Group. And as a member, we were invited to join as a member and support some of the educational efforts. And there is the AIX 360, there's the AIF 360, and the uncertainty quantification. I think there's also another new project called MLX, for which Animesh Singh from IBM is going to be presenting. His team is going to be presenting in the next few weeks. So I thought it would be a nice effort to understand the theoretical foundations and also the research strengths on how this work is being thought about by industry practitioners and also by researchers, but also connected to practice on how these could be actually implemented and realized. Uncertainty quantification is a very fascinating topic for me. And going back to my engineering days, I was always looking at, from a statistical analysis perspective, how you could quantify uncertainty in various ways. And model risk, as you know, in the financial world is all about quantification of uncertainty. But I think the theme here in the quantification in the context of machine learning is very intriguing. And I'm very interested to know more about Umang's work. So welcome, Umang, for this amazing workshop. And as all of you know, the protocols are the same. Feel free to use the chat window, Q&A window to type in any questions. We'll be periodically pausing and answering questions along the way. So this session is a 2-hour session. So you can grab your lunch, and if you're in the East Coast at least, and settle down, or if you're in other parts of the world, get your coffee or your dinner or whatever is your favorite drink or beverage or food to have along with that. But also, I want to make sure that you are also, some of the links which we're going to share. There are some really good white papers and research papers you can read through. And next week, we have another session on machine learning security, and Navdeep Gill from H2O.ai, and he had done some work with Patrick Hall, who was at H2O, but now he's at BNH.ai. So they had put some work together on machine learning and security related aspects. So that session is going to be from 12 to 1 next Tuesday. And as you know, there are multiple sessions happening. So please sign up at qsummerschool2021.splashback.com to get any updates about future sessions. And all these sessions will be available on Pure Art Academy for people who know how to get there. We'll also post some links in the chat window so that you can join us both online and offline. So without further ado, I would love to welcome Umang to the virtual stage, and please take it away, Umang. So let me just make sure that you can share your screen. Okay. So Umang, the stage is all yours.
Great. Let me share my screen before I do anything else. Okay. Sure. Wonderful. I think you guys can see me, I hope.
Yes, we can see.
Great. Just if I periodically look over my shoulder, I'm looking at a separate screen I have where I'm hoping to see you guys and your questions. So Shri, thank you for that introduction. As Shri mentioned, my name is Umang. I am a PhD candidate in the machine learning group at the University of Cambridge. I'm also currently a fellow at the Mozilla Foundation and a student fellow at the Leverhulme Center for the Future of Intelligence.
So Umang, can I request one thing? I think your presenter view is being shared.
Shame. That's a shame. So I just realized that. Yeah. Let me write that very quickly. Give me 2 seconds. Perhaps this will work. Oh, it's still, give me 1 second. I'm just gonna pull this out.
I think you can do a switch. There's a top icon. You can switch the screens.
Yeah, I think if I pull it here, I'm gonna.
How about you do that again? I'll show you an icon. I think there's an icon which lets you do that.
Yeah,
so
I know this classically.
Okay.
This classically will work in 1 second as soon as I figure out how to move this down a little bit. Okay, cool. So this should be fun.
Okay.
Maybe you can see yourself, which might be annoying, but I hope. Can you see yourself?
Yeah. No. Now it's perfect.
Oh, perfect. Great. So So sorry about that confusion. But the title of today's talk is going to be Challenges and Frontiers in Deploying Transparent Machine Learning. So as Shri mentioned, I think we've circulated a few papers, 2 for the first half and 2 for the second half. But if you have any questions, then feel free to shoot me an email, message me on Twitter, or reach out in any way, shape, or form. I'm happy to answer questions and continue a lot of this discussion offline, as I will be flying through lots of material today. So with that being said, I'm going to jump right into it. So the talk is broken down into 2 portions. The first is called Challenges with Explainability. It's going to cover a lot of the work that we did over the past 2 years on understanding how explainable machine learning is used in practice. And the second part is going to address one of those challenges, and it's going to be titled Uncertainty as a Form of Transparency. So without further ado, we'll jump into the first part. So our starting point is about May 2019, when we asked the following question, where how are existing approaches to explainability actually used in practice? So over the last decade or so, you've seen a lot of different approaches to explaining machine learning output. We really want to understand what are people using in practice and how are developers and end users actually benefiting from these tools. So this first work was kind of done jointly with lots of authors from lots of institutions. The title of that paper was Explainable Machine Learning and Deployment. It appeared at the Fairness, Accountability, and Transparency Conference in 2020 in Barcelona. And when we started that work, the first thing we noticed is that there's a huge growth in the transparency literature. There's so many algorithms that are proposing, well, we can explain a machine learning model output in various ways. And our question, what we really wanted to do is study how organizations use these algorithms, if at all. Before we even start with this direction of understanding how people use it in practice, it's important that we have a shared language to discuss what do we mean by transparency and what do we mean by explainability. So when I refer to transparency, and for all intents and purposes of the work that we perform and much of our community performs, we view transparency as sharing information with stakeholders that is relevant to how the model actually works. So this might be documentation telling you about how the model was trained and some of the information about the socio-technical infrastructure that surrounds the system. Honestly, releasing code is a form of transparency. Now, albeit it might not be interpretable or understandable to a lot of people, it is one form of transparency. And the form of transparency that I'm most excited about is what I would call algorithmic transparency, understanding various properties of the system that you can expose to end users. And explainability is one specific form of algorithmic transparency where we provide insight about a specific data point. More specifically, how does the model behave on a given data point, right? So our approach to studying the industry was looking at performing a 30 minute to 2 hour semi-structured interviews with a bunch of individuals from various corporations, nonprofits, academics, to really understand how these approaches are actually used in practice. How are they affecting the day-to-day activities of a data scientist? So we talked to about 50 individuals from 30 organizations. A lot of this work was done jointly with the Partnership on AI, which has a huge membership body that gave us access to a lot of these organizations. So some of the questions that we asked were, well, what types of explanations do you use? Feature-based explanations, sample-based explanations, counterfactual explanations. I'll get to that in a bit. Who's the audience for these model explanations? Are you giving it to domain experts and product managers, or is it just something research scientists are playing around with internally? And then in what, most importantly and most interestingly for me, is in what context were these explanations deployed? Are they informing like your development process? Are they helping some end user make decisions? How is it actually being used in practice? So when we conducted this study, we found that by and large, there are three very popular explanation methods that are used in practice. The first is feature importance, which attempts to attribute value to each individual input feature that is fed into a machine learning model. It asks the question, what happens, which of these input features is most important for a particular model output? So if I were to tell you my age, my blood pressure, my weight, and I asked you if I have a fever, we'd hope that you'd look at my body temperature when making that conclusion, right? So my age likely is not relevant. Maybe some would say that very young children are more prone to getting a fever. Weight is in the same kind of category, but body temperature is the one thing that matters. It is the most important feature that we as individuals know is important for predicting if someone has a fever. Therefore, we hope that our machine learning models kind of mine that same kind of feature importance. The second type of explanation that's very popular in practice is sample importance. So if I train a machine learning model on lots of training data, I might want to understand which of my training data points is influential when doing prediction on an unseen test point. So a new patient walks in the doctor's office, and this doctor might actually think about the previous patients that they've seen in the past. They're actually doing sample importance or training point importance, just trying to kind of see what in the training data is influential to the new diagnosis or prognosis that we'll give today. So there were lots of methods for doing this that I'll also jump into, but by and large, it's important to remember that these two are very popular in practice. The third type of explanation, which is becoming more popular, is counterfactual explanations. So counterfactual explanations ask the question, what do I need to change about an input in order to change my outcome? So if I went to get a loan from a bank and I told them a bunch of information about me, they might come back to me and say, if your income was $10,000 higher, I would have given you a loan. The counterfactual reasoning there is if this, then that, right? So if I were to make an intervention on you today, all else constant, I can get a desired outcome from a machine learning system. Just three types of explanations are popular in practice. And the three types of explanations are actually consumed by four different stakeholders. So the stakeholders who are consuming these explanations include executives. This is quite interesting for folks who are involved in large organizations where a lot of executives enjoy the rhetoric that goes along with explainability. It's important to say you're transparent. It's important from a business standpoint, from a corporate social responsibility standpoint. Executives loved the idea of explainability. Now, whether they gave proper guidance to their developers on how to operationalize it, that's a completely different story. That's kind of why these tools like IBM AIX 360 is really nice, because it allows people to like build these kind of explainability algorithms directly into their systems, cap them from PyTorch at Facebook. They do the exact same thing. These are really nice tools that people can play around with. But executives love the rhetoric that goes along with explainability, and they had a vested interest in actually understanding how these systems work. The next type of stakeholder that's at play here is an engineer. An engineer might want to actually know how is their system, how does their system work? Does it adhere to norms that I know? Like, have I fit my fever model to age? Right, an engineer kind of can use explanations as a form of debugging. And then the third type of explanation that's really popular is the third stakeholder that's really popular is end users. So end users are those that are consuming the output of machine learning systems. And by and large, we found that very few people or very few end users are actually looking at explanations. So while the motivation is there, while it makes a lot of sense to show explanations to end users, very rarely was someone who is a layperson or not really, who doesn't really understand machine learning, very rarely were they shown explanations. And we can talk about why and how, and there's lots of interesting work that's going on in this direction to make explanations tailored to end users. And then the fourth and final stakeholder was regulators. So regulators loved the idea of explainability as well. So our findings were threefold, and I'm going to kind of like fly through them.
Can I interrupt you for a second?
Of course,
are you differentiating the difference or the discussion about explainability versus interpretability, or are you using them interchangeably?
Yeah, really great question. So I'm not using them interchangeably. I personally don't really like the term interpretability. I think that explainability captures a little bit more of what we want, which is or at least of what I want, which is to provide a form of explanation or transparency to an end user about the model's behavior. So you can even recast fairness as a form of transparency, especially if you communicate those fairness needs to end users. So this is kind of going to come down to what we talk about later, which is like, if you're communicating a piece of information about a model to an end user, I view that as transparency. Explainability has a role in that. Interpretability may not, right? Interpretability might be, I have a really simple machine learning system, and that's great. And that's really important in certain domains. But here, explainability is really saying, like, can you provide me with some sort of justification or explanation for what the system is doing? And that has implications on the regulatory front, the policy front, the end users, and the interesting psychological questions as well about conveying explanations for why the model is behaving. A sparse model is interpretable, but it might not have a nice explanation that it can provide to an end user.
Okay, thank you.
Yeah, feel free to ask questions if anybody else has. I can't see the chat right now, but sure, you can let me know if anybody has any questions.
I'll be monitoring the chat in case there are any questions.
Wonderful. So our findings are threefold. The first is that explainability is primarily used for debugging internally, right? So this idea of looking at these explanations was kind of used by data scientists internally to debug their systems. The goals of explainability are not necessarily clearly defined within organizations. And most organizations, again, like I was saying, like if some executive loves the rhetoric that goes along with explainability, you found organizations that wanted to engage with explainability but didn't necessarily know why they were doing it or how to actually go about providing those explanations to end users or other stakeholders. And then the third is that there are technical limitations that make explainability very hard to deploy in real time, right? So with these three findings, I'm going to quickly like whiz through some details about each, but I want to jump along to some other work that kind of spins out of this. So with respect to explainability being used for debugging internally, we found that the most popular explainability method was feature importance, and actually very specifically Shapley values. So there's a really nice repository for those who haven't seen online called SHAP. And arguably we found that people liked the fact that it was really well maintained. It had a really well maintained repository that allowed a lot of developers to kind of plug and play these feature importance on top of the models that they're already training. But in actuality, this didn't really correspond with what people really wanted in practice. It was just really easy to use. So as a debugging mechanism, people could play around with the Shapley values and Shapley plots, and there's lots of other work in the research community that has kind of gone in this direction, some of ours included. But it's not clear if the new advances actually help us bring these explanations to end users or have it actually play a role in practice. With respect to the goals of explainability not really being clearly defined within organizations, in our interview study, we basically came up with a way for people to establish these explainability goals within their organizations. The first might be identifying the stakeholders, figuring out who's going to consume these explanations. The next is engaging with those stakeholders to figure out really what is the purpose of that explanation. Is it to debug? Because if it's for debugging, like there might be a different type of explanation you need. Is it some sort of justification that you need to hold up someday in the rule of court, in court? The needs of each of the stakeholders will vary with respect to the explanation. And the last is think about what that workflow will be. And there are details on all of this in the paper. Obviously, it's a very, very high level, zoomed out view of it, but I encourage those that are interested in this particular work to check out the paper. With respect to the limitations that exist, we find that feature level explanations may not help expose spurious correlations. There's been a plethora of work since we've written this work, since we wrote our fact paper, that kind of explores this idea of spurious correlations kind of sliding by feature level explanations. So feature level explanations are not really good at finding these spuriously correlated signals that might appear in inputs. We find that there is a desire for causal underpinnings to models, and then there's also a desire for causal explanations, but you can't have a causal explanation for a non-causal model. So there was this kind of tension between the desire to use large-scale deep learning models but then have causal explanations, which may or may not be feasible. So there are some limitations in terminology that needs to be clarified with respect to the causality. Some other limitations included sample importance being computationally infeasible. Salesforce actually worked on this problem since we wrote this paper. They have this new library called FastIF that came out earlier this year, about a month ago maybe. And they're trying to think about how can we can we quickly search over our training data to figure out which of the training data points is influential to new test points. And communicating that to end users is valuable, but we just didn't have methods that allow us to do it in real time. And the last one would be that there are privacy concerns. So if I do provide you with simple gradient-based explanations, Smitha Milley and team at Berkeley, Moritz Hart actually, and all the students, they basically showed that, look, like if you give me access to gradient-based explanations, I can actually learn your training data. And I give you like a finite number of queries. I can actually learn your training data, which didn't leave the privacy NGOs that we spoke with very happy. So it's important to kind of realize that there might be privacy concerns with providing transparency in the first place. So with all of these findings, we basically decided to hold a convening amongst a bunch of individuals. Now, the title of our summary of our convening is called Machine Learning Explainability for External Stakeholders. The convening was jointly held by IBM's Trustworthy AI team, Partnership on AI, and the Leveroom Center for the Future of Intelligence. And what we basically did is we were like, look, like it doesn't seem like explainability at the moment has clear goals. So let's bring a bunch of stakeholders from a bunch of different organizations together to kind of think about, let's kind of like hone in on what are the important questions that need to be answered in the explainability world. So we had 33 participants from 5 countries, 15 were ML experts, 3 designers, 6 legal experts, and 9 policymakers. And the domain expertise varied from finance, healthcare, media, and social services. Social services being someone in a governance organization or kind of part of the government itself. And our goal was to facilitate like an inter-stakeholder conversation around explainable machine learning, such that we can come up with concrete goals that explainable machine learning can have in the future. So I'm going to jump to like the 2 takeaways that we had from the day, and I've left them as open questions that hopefully people in this call are excited about and can tackle. But it also motivated a lot of our future research. So the first thing that we learned is that community engagement is very important when you're doing explainable machine learning. Specifically, it's important to understand the context in which explanations are going to be used, right? Does the context change the properties of the explanations that you expose? Now, on the next front, it's not clear how explanations should be evaluated, both on the quantitative and qualitative front. And it's important to work with stakeholders to kind of think about what are the ways in which you can evaluate such explanations. Now, one of the interesting things, anecdotes that came up in our convening is that if we provide explanations to certain subgroups or certain individuals, we might end up having preferential treatment. So we can imagine if we had a rental application machine learning system and we were providing explanations to people on what they can change about their input in order to get approved for renting a particular apartment. Someone who is a broker for example, might have preferential treatment because they know how to act on the explanation, while another person might not. Right? And really understanding that there might be data misuse and preferential treatment that occurs. These are ideas that I, as a machine learning practitioner, might not have come up with, but speaking to practitioners, speaking to individuals who are working with the New York City Housing Council and working with a lot of these civil societies, like these kinds of questions and ideas and societal implications from this. And then how can we actually educate external stakeholders regarding the functionalities of explanation? How do we educate people and tell them that they do have access to explanations, that if they are being treated by an algorithmic system, they have the right to an explanation, as GDPR has kind of taught us. And then for data scientists, how can we actually tell them what are the limitations associated with explainable machine learning? Right? It's not a silver bullet. There are a lot of shortcomings, and we're going to discuss some of these shortcomings coming up. The other thing that we notice that's really important with explainability is really understanding very, very carefully, how do you deploy explainable machine learning? So the first question that came up is, how does uncertainty in the model and uncertainty that might be introduced by the explanation technique actually affect the resulting explanation, right? So the model itself might not necessarily be highly accurate. It might have high uncertainty. How does that affect the explanation? And then the second thing that came up is, how do stakeholders actually interact with the explanations that result from the system? This is something that I find very interesting, and this I won't be talking about today, but we do have ongoing work in this space where we're thinking about, given a form of transparency, how does a stakeholder, an end user and developer, actually interact with the system such that they can incorporate their feedback on the explanation back into the learning system? And this is really interesting because explanations have kind of turned into this conduit. We're assuming you're going to get an explanation. And actually, we don't want our explanations to be deceptively gamed, as we'll talk about later on. We actually want our explanations to be faithful, such that someone can come in and intervene and tell us, you know what, actually, body temperature is the most important thing for our fever model. Why don't you go in and change your model? Right now, we don't have a way of doing that. And anybody that tells you we do is selling you snake oil. So it's really important to be very careful when thinking about how you're going to deploy these systems. And then two other questions that come up on the deploying explainability front. One is, how will stakeholder behavior change? So tomorrow, if a bank tells every rejected applicant that they can make a $10,000 more and I'd give them a loan, well, what if everybody comes back the next day with $10,000 more in their bank account? How does stakeholder behavior change, and how does that actually affect the model itself, being the third question? So over time, do our explanation systems help us figure out how our models need to adopt to the changing recommendations that we're providing to people? Right? So community engagement and careful deployment of explainability are extremely important. And these are kind of the relevant takeaways that we had from that convening. But what this let me do is ask what I call practitioner-driven research questions. So in talking to practitioners and the heads of explainability for all major tech companies and startup CEOs who are thinking about developing ML ops companies, it allows me as a researcher to ask questions that are very pertinent to practitioners. And I'm going to walk you through in the rest of this first half on three questions that we asked, and then the three results that we got as a result of asking such questions. So the first question that we ask is, can we actually provide practitioners with a methodology for evaluating explanations? The second question we ask is, can existing explainability tools be used to identify model unfairness? So this kind of stemmed directly from our convening. And the third is, can we quantify how much uncertainty is associated with the given explanation? And this will dovetail into our second half of our talk today. So we'll start with that first question. Can we provide practitioners with a way to evaluate explanations? So this paper appeared at the International Joint Conference on AI in 2020. It's called Evaluating and Aggregating Model, Feature-Based Model Explanations. So you may or may not be familiar, but there are lots of really common feature-based explanation methods. And I'm going to walk through some of the formulations of them here. And don't worry if the formulations don't make sense or if they're not necessarily helpful. They might be TMI, but on a high level, it's important to understand that there are lots of different explanation methods that have appeared over the last decade. So a really, really popular one is called LIME, which tries to fit a locally linear model that's tangential to the decision boundary of a non-convex or non-linear model, and then uses the weights of that simple model to explain the machine learning system, right? So it has a local surrogate model. Another method is called SHAP. Shapley values use a game theoretic notion to assign value or attribution to various input features. Recall the types of explanations we're thinking about here are rankings of features. I'm trying to figure out, assign a scalar value to each individual input feature. So it might be a pixel of an image, it might be a word in a sentence, it might be a node on a graph, it might be a specific measurement when it comes to some time series data, like a particular time instance. I'm trying to figure out how important are each of these different elements for my final outcome of a black box machine learning model F here. So G is our explainer, F is our the black box model we want to explain, and X is the input at which we're getting our explanation. This is all detail. These are all details that may or may not be relevant right now, but the thing to kind of take away is that there are multiple methods. And the last method appeared at ICML in 2017, which is called integrated gradients. They basically accumulate, they use path gradients to figure out how much a model's attribution kind of varies between baseline input and the output that you actually care about. But again, the thing to take away here is that there are lots of different methods that in the last 5 years that have kind of like spun up as a result of this. So the question that we ask is, how do you actually evaluate these explanations, right? So we come up with some criteria and we aggregate some from the literature. So the first one I want to discuss is sensitivity. So do similar inputs have similar explanations? So if I didn't change much about a specific input, how much would my explanation change? So this is analogous to like getting a Lipschitz constant. What you look at is in a R-sized ball around the explanation, around an input that you want to explain, how much does my explanation vary? And we could also look at how much maximally in that R-sized ball does it vary, right? So this is like a very standard notion, a notion that we can codify and a practitioner can implement very, very easily. Another evaluation mechanism might be faithfulness. So if I give high attribution to a given feature, I hope that the feature that I've given high attribution to is the one that actually matters for my model, right? So we use a variant of the Pearson correlation coefficient to kind of calculate what happens if I mask out some of my features. Does the attribution that I've given out to masked out features correspond to the drop in predictive performance, right? So faithfulness, is my explanation faithful to what is truly happening in my model? We propose another explanation evaluation criteria called complexity, which says how digestible is my explanation? Is it something that's super complicated? The most complicated explanation in terms of feature-based explanations would be one where every single feature is given equal attribution. That means every single feature is equally important. Now, this might be the most faithful explanation, but in terms of digestibility, it might be very hard for someone to understand that every single feature is really important. So one natural way of measuring that is first by defining a probability distribution over the attribution, so normalizing, and then taking the entropy of that said distribution, right? And that's kind of what I show here. So again, the most complicated explanation would be one where every single feature is equally important, which is kind of useless, but again, it might be the most faithful, right? It might be the one that captures the the model's outcome the best, but it might be, it is quite complex for someone to understand. So now, given these mu's that you've been seeing, the complexity, sensitivity, and faithfulness, we thought, well, can we actually think about how to aggregate explanation methods with respect to these mu's, right? So can we develop aggregation functions or functions that help practitioners kind of decide from this huge suite, this ever-growing suite of explanation methods, such that they can learn an explanation that maximizes the criteria that they care about. Now, this criteria might come from an end user, an executive, or whoever it might be, or it might be a criteria that's just nice to have, right? That maybe if I just change one thing, if I just change my age ever so slightly, my fever predictor shouldn't change very much. My explanation for fever should not change very much. And that's kind of what sensitivity measures. So we, in this paper, kind of then go on to study the ways in which you can aggregate a bunch of different explanations from, like, let's say, Lime, Shap, and integrated gradients to kind of learn an explanation that maximizes the said criteria. Right? So, I'm going to talk about 3 candidate ways to combine explanations. One might be doing a convex combination between 2 explanations. Another might be centroid aggregation, which is just a fancy way of saying taking a mean or median of the explanations. You could also do rank-based aggregation, which I find very natural. Rank-based aggregation is the idea of taking rankings of features. So if fever was strictly more, if body temperature is strictly more important than age, and age was strictly more important than weight, then I can somehow aggregate those different explanations from Lime, Shap, and integrated gradients, and then obviously other methods. So centroid aggregation is quite interesting. And then the other idea that we don't really study is the idea of doing like Bayes opt to learn this model. Now that might be overkill, some would say, but it is possible, and it's not too difficult to do. So the idea that the takeaway from this kind of paper is that, look, like we were able to kind of say that aggregating explanations locally is very useful using classical rank aggregation or convex combinations. In the paper, we go on to show that aggregating Shapley value explanations results in a Shapley value explanation. And then we show that you can learn aggregate explanations via one of the procedures that I just mentioned on the last slide to lower sensitivity or lower complexity. So the sensitivity of the aggregate explanation will be provably lower than the sensitivity of Lime-Shap or integrated gradients, which is a nice result, right? But the thing to think about here is what we've done is we've taken a practitioner-driven research question and kind of gone and turned it into this nice like quantitative research, like machine learning research, that then directly answers the question that practitioners have, which is amalgamating results of how do you evaluate different explanations, right? And I'm really excited by this kind of idea of taking practitioner questions and turning them into concrete research questions that we can ask. That kind of answers that first question. So from here, I want to talk about the second practitioner-driven research question we asked, which is, can explainability tools actually be used to identify model unfairness? So I remember sitting at that convening. It was the last in-person convening I went to before COVID hit. It was in February 2020. And at that convening, I met some regulators, and one of the regulators had this interesting idea when I told them what feature importance was. They were like, well, if the sensitive attribute or the protected attribute appears in my explanation, then my model is unfair. And we were intrigued by this question, so we decided to actually study it. Is this actually the case, right? Is my model unfair if my sensitive attribute is important to my model, okay? So for a regulator, the reason they were asking about this is, well, if I can just look at the explanations, it's a very interpretable and explainable thing to do. Look at the explanation, see if the sensitive attribute has high attribution, and if it has high attribution, then maybe this model is unfair. And we basically decided to study this question. And the short answer is no, you cannot. And we'll talk about it. So this is a paper that appeared at the European Conference on AI in 2020 called You Shouldn't Trust Me, Learning Models Which Can Conceal Unfairness from Multiple Explanation Methods. So again, why do we even care about this problem? So on the left-hand side, you see model A, and you see for a given input what its feature importance scores are. Let's say the task, you were given 3 features: the money someone spent, the age of an individual, and the time spent doing some arbitrary task. Now on the left-hand side, you see model A gives attribution to age, which means that it is using age in its calculations, right? And on the right, you see that model B does not use age, which kind of apparently makes model B look fair. So if someone were to glance at these explanations, model B is actually fairer than model A because model B is not using age, which is a protected attribute in the US. Okay? It's a sensitive attribute that we can't necessarily use when making predictions for machine learning systems. So what we ask is, given an arbitrary—
Can I there for a second, Umang?
Yes.
Won't that all depend on how you define fairness in this particular? I mean, like, for example, if I'll take a random example here, right? So I'm just kind of saying, okay, so priority for boarding a flight, right? So there, age is an important factor. I want to prioritize really young kids or maybe really older people. And then age, there, I guess it's a fair assessment. And, letting the really old people or really young people get on the flight. I mean, at least like, normal human standards, if you will.
Yeah, sure. So there's a really interesting moral question there that I think you bring up. So with respect to the Fair Housing Act in the US, you actually are prohibited from using a bunch of sensitive attributes, which include like age, race, and these kinds of things. So the machine learning community has kind of co-opted that to mean that any of these sensitive attributes should not really be used by the system. Now, there's been a lot of work on like the fairness by unawareness community, which says, what if we just drop the sensitive attribute? Don't even use it, right? It's just like, it gets rid of our headache and gets rid of the headache for the government as well. And people have shown that that's not necessarily a good thing to do. With that being said, more often than not, if you might have apparent discrimination. And I think we probably wouldn't word what you said like discrimination, but what you're saying is it might be okay to discriminate in certain settings, right? And it's when you're going on a flight, it makes sense to discriminate and let the older people and younger people on first. Like that is a sensible thing to do. We would never word it like that, but that is kind of what is being inferred under the hood. So here in this setting, what we usually try to say is like, look, can we develop models that apparently don't look like they use this feature? And the idea is that I could come up with an airline prediction system that helps you get people to board on planes and basically come up with a system that looks like it doesn't use age. And that's basically what we want to do. Because if I am discriminating on people by age, right, and providing them a priority, someone could actually complain and sue, let's say United, by basically saying, look, United, like you're discriminating against me because I'm middle-aged, right? I'm not old or young. And or what we're basically studying here is that how can you kind of mask that unfairness? So what we're actually doing is a very malicious thing here, but we'd rather do it in a setting of research rather than having someone else do it and actually deploy it in practice.
Okay, and the second question is, you're assuming that all these features are independent?
No, I don't think you need that assumption for what we're about to do. No, you don't need that assumption.
So what if, even though, I mean, let's say the third feature and the age is highly correlated, then
so I think I heard you correctly. So you're saying that if they're highly correlated, then this might not necessarily be a good thing. Right. And yeah, we study that and we find that might be the saving grace of this kind of method. And I'm going to talk about this particular work is what shaped my perspective that fairness is a form of transparency. And I'll jump into why. Because an explanation in and of itself is insufficient for communicating fairness goals, but communicating fairness metrics instead of communicating explanations to these regulators would have sufficed. So I could have just communicated these fairness metrics to them, again, in a way that they can understand, which right now, equalized opportunity, equalized odds, those kinds of things are not necessarily palatable for regulators or end users. But if we can come up with ways to communicate that information, then we can actually build systems that are transparent about where it's fair and where it's not fair. So proxy features are probably the one thing that save us in this kind of setup.
Okay, cool. So thank you.
Yeah, so the big idea that we have underlying all of this is that how can we manipulate explanations? So there's been a lot of work recently on, can you modify an explanation via an adversarial perturbation of the input? So a lot of people say, well, I can take an input, add some noise or add a specific type of noise to it, and my explanation, so my output of G might vary. And this is quite sensible, and there's a long line of work kind of doing this over the last couple of years. More interestingly, what you can do is actually perform an adversarial perturbation or adversarial attack on the model's parameters. And we're going to leverage this as our tool for getting our modified explanation as we design. So there's this one work from Juyan Hyo at NeurIPS. Juyan will be joining Cambridge soon. And Juyan showed that if you perform an adversarial attack on the parameters, you can actually control a visual explanation to be arbitrary. Right? And that's actually quite nice, because what this tells us is that we can learn a adversarial perturbation of the parameters and basically mask this unfairness from the explanation. Mask in the sense that make it seem like fairness, like the sensitive attribute is not being used. Right? So the setup is we have this classifier F that maps from some input space X to Y, an explanation function G that gives us a ranking or a scalar attribution over features. The jth feature is going to be our sensitive attribute. And our goal is to learn some, and our F is parametrized by some theta. We want to learn some delta, right? Some delta perturbation to our parameters that give us two properties. The first is the model should be similar. That means the perturbed F, so the attacked F, should have a similar output to the original F. And the second is that we want a low target feature attribution for our sensitive feature. What does this mean? This means that the amount of attribution given the gradients or the amount of attribution at the sensitive feature in our attacked model should be lower than that of the original model. And as such, we propose something called the adversarial explanation attack. We take a vanilla loss function And then we say, once you've trained your parameters to theta, we now help you learn delta. And delta is a function of like your normal cost entropy loss plus what we call the explanation error term. We actually get away with just penalizing the gradients of the loss with respect to the input features sensitive attribute. So with respect to the sensitive attribute. And what we find is that is the following. So I'm just going to jump directly to the results of how our attack works. So on the left-hand side, you see the original model, and you see for multiple explanation methods as listed across the rows. I'm listing the ranking of the sensitive attribute with respect to that explanation method, the magnitude of the ranking of the sensitive attribute. I'm listing them in here, the ranking, and then I'm observing that they kind of all are quite high, right? For gradient times input, if you see, like, you'll see that, oh, it's actually quite high. It's around 2 to 3. It always appears like as a second or third most important feature, right? And then we perform our attack and we see that ranking decrease. And what does this tell us? This tells us that we've achieved what we wanted, which is get low relative importance for the sensitive attribute. It generalizes to test points. So this is reported over the test points, and this transfers across multiple explanation methods. So even though we're only penalizing for the top, for the gradient-based explanation, we actually see the result even in Shapley values, which doesn't even use gradients, even in Lime, which doesn't even use gradients, right? So we actually see this result kind of manifest everywhere. And though we don't theoretically study this, and there are other folks after us that have, it has something to do with us finding a local minima where the gradients in the direction of the sensitive attribute are quite low, okay? In our findings, just to kind of jump through this, is there's little change in accuracy, but there is a detectable change in outputs. That might be the saving grace for us kind of doing something like this. And there's low attribution that we achieve across multiple explanation methods for a sensitive attribute. And one of the things, going back to Shree's point, is that it's important to recognize that this form of explanation that a regulator had, right? This idea that a regulator had to take an explanation method and use it to see if a model is fair or not is not necessarily a very good thing, right? The fairness metrics might be the thing we need to communicate to them, even though there'll be a high barrier to entry for them to understand sometimes what these fairness metrics might imply, right? So it's up to us as practitioners to come up with ways to communicate that information to other people. So that's kind of this work in a nutshell, right? So coming back to our second practitioner-driven research question, we basically identify that existing explainability tools may not be able to be used in their current form to identify model unfairness. And then this brings us to the third question that we ask as a result of those convenings and as a result of that first interview study I ran in summer 2019, how much uncertainty is associated with explanation methods. So a lot of individuals were wary of explanation methods. Therefore, it might be helpful to quantify how much uncertainty is associated with explanations. So we studied this with Quantum Black. Quantum Black is a subsidiary, the data science subsidiary of McKinsey. And we published this paper at AAAI workshop this past year, and it's called The Effects of Uncertainty on the Quality of Feature Importance Estimates. So again, our motivation here was to answer that question that we obviously got from the practitioners, but we noticed that there are a lot of vulnerabilities that are associated with feature-based model explanations. Not only our group, but Hima Lakaraju's group at Harvard has found a lot of similar things. And then lots of other groups have kind of been thinking about this. So there are a lot of vulnerabilities that are associated with these feature-based model explanations. So it's important to kind of quantify the uncertainty associated with the explanations we generate. And then the second thing is that the practitioners might actually use these explanations for model selection, right? Which might lead to some kind of confirmation bias, some sort of over-reliance, or even manipulation, right? So I can find a model that has the explanation I desire. Now, this is kind of directly relates back to what we talked about last time, which is we just masked unfairness, which means who knows what else we can do in terms of manipulating the explanations to have the desired effect, right? So I'm going to kind of like very briefly gloss over like the methods and then kind of jump to the implications. But the assumptions that we have for the methods that we provide are, the first one is that a lot of assumptions that we have in machine learning for the most part is that there's a fixed model that's good, right? So we say like, look, I have an explanation. I have a single point estimate model that I get. I just train a deep learning model with a fixed seed, and I obtain a set of parameters, and I'm going to deploy those parameters in the cloud, and SageMaker makes it really easy for me. And great, now I can generate explanation from it. But the explanations that I generate have this strong assumption that there's only one suitable model, which is way too restrictive. And now in actuality, you can obtain multiple point estimates or multiple models by subsampling from the models. For the same model class, the same parameter setup, and the same model specification, you can vary this. You can subsample from the training data set, or you can vary the initial seed to kind of obtain these uncertainty estimates. Kind of very similar to getting uncertainty estimates via bootstrapping. What you actually really want to do is we want to be Bayesian about it and kind of marginalize over our posterior. But sometimes that's not always doable, especially with the types of systems we use, right? So the motivation here is that, look, there are lots of really good models, and we just happen to select one. Therefore, not only is our explanation probably not very good, but we should probably study how the explanation varies over the set of all good models, right? So the Shapley value, if you think about it again, is a way of attributing value, phi I, to an individual feature, right? Don't worry about the actual setup, but effectively what we're measuring is what happens if we add this feature that we're interested in to arbitrary inputs, basically, arbitrary sets of the subset of features. Now, what people forget is that the Shapley value has this implicit dependence on f, which is the actual function that you've trained. So what we can actually do is we can quantify the variance of the Shapley value over these different f, right? And that's kind of what we do down here. Again, like the details are in that work, but I'm really excited to tell you about the implications of what we find. Maybe not necessarily the machinery to get there, but we can quantify the variance of the Shapley value over a bunch of functions f, right? Basically, our bunch of subsampled models that we got. So our approach, in the truest sense, is we actually want to marginalize over all possible models. Now, obviously, for those that are familiar, it's very tough to do this. So what we can do is we can just basically sample a subset of models, B, and then basically average over that subset in a weighted way, okay? And what this allows us to do is obtain an estimate of the phi star, which is the true Shapley value over all possible models that I could have learned given the current setup. And then the variance can be redefined in terms of this quantity. Okay, so this is like a new explanation evaluation method that allows us to quantify the uncertainty associated with each of these different input features. So the first finding that we have is that predictive uncertainty in the input leads to high variance in the explanations. So what do I mean by this? Let's walk through this. So for the adult data set, what you're viewing here is the explanation for 2 points. On the left-hand side, that's the most uncertain, right? The most uncertain point is the one that has the highest variance in the predicted probability across all possible models, okay? And the least uncertain one is the one that has the least variance in its predicted probability. That's what we call uncertain. Now, what you're seeing here is how is that Shapley value distributed over all of those models? And in the setting of being most certain, you see most certain, so least uncertain, you see that the Shapley value is rather consistent for a bunch of different methods. By the way, there's like 4 or 5 different methods and approximations here. But what you're seeing is that for points that are very uncertain, very certain to my model, so least uncertain on the right-hand side, the explanations are basically constant, which implies that the model itself is quite confident in this model selection, but also in the model class that's been picked, right? Because the explanation is a good explanation that kind of captures the true relationship across all possible models. However, if you have a point that's really uncertain, so this might be a point that's out of distribution, right? What you'll notice is that there is a huge range of Shapley values that are valid, right? And this is kind of scary, right? Because this means that how do I? All these models are really good, right? They're all equally good, right? For the most part. How do you select? I mean, if you look at some of these, the attribution given to age can vary from positive and negative, So how am I supposed to know which model is the right one to select? So the existence of this uncertainty is actually kind of a red flag for us, because it tells us that predictive uncertainty can lead to high variance in explanations, which means I can actually manipulate these my model selection to get the explanation that I desire, which is quite scary. So that's the first finding. The second finding is that uncertainty actually degrades the quality of explanations across all metrics. So if we go back to those evaluation criteria that we aggregated in the first section, right, in the first practitioner-driven research question for our IJCAI paper, and then we look at the performance on in-distribution versus out-of-distribution points. So another way of saying we have a rejection threshold for certain and uncertain points. We find that the quality of explanations that we get for out-of-distribution points is significantly worse than that for in-distribution points, which means that it is probably detrimental for us to use explainability on out-of-distribution points. So we need some sort of other mechanism to think about transparency, because explanations are probably not the right thing, right? Because explanation quality is quite bad. So that kind of is kind of our second finding. So what do these findings imply? The first implication is it actually might make sense for data practitioners and to actually consider the entire distribution of explanations as opposed to considering just a point estimate. So right now, what people are doing is they are training a single model, and they're taking that single model, providing an explanation, and that explanation is one configuration from this entire distribution. Now, that to me doesn't seem quite summative. What you really need is to somehow show this distribution to domain experts or to data scientists who have kind of an understanding of the domain they're working in, and let them select the model that they want. So an explanation might actually become a model selection method that you can use. And that kind of will help us and save us in the settings where we have got guarantees that our data is from the same data distribution that I trained on. So I have in distribution data, but for out of distribution data, what are you supposed to do? So for when you have feature importance on uncertain data, we actually suggest that don't actually do that. Don't actually provide feature importance on uncertain data because it's quite unreliable. Instead, use counterfactual latent uncertainty estimates, also known as clues, which I will be talking about very soon, because that was a work that we did as a result of this paper as well. So that brings us to our second implication. But by and large, what we were able to do with this work is quantify how much uncertainty is associated with these given explanations, such that now we have these practitioner-driven research questions that we can ask, thinking about evaluation of explanations, how unfairness and explanations interplay, and how much uncertainty is associated with explanations. And so that kind of concludes the first half of today's talk. I hope I've convinced you that there are a lot of challenges associated with explanations, and the only ways that we were able to raise them is by talking to practitioners, which is kind of what led us to a bunch of really interesting concrete research questions that we were able to ask. So now I guess we can take 5 minutes of questions before jumping into the second half. Vedant, I think you have your hand up. Sorry, I can't actually see. Cool, I'm just gonna come here. Okay. Cool. How does SHAP and Lime work for a deep learning model? That's the first question I got. Okay, great. So there are a lot of things that we can discuss here. The way they affect a deep learning model. So for a deep learning model, like you can get a Shapley value approximation quite easily, right? Because what Shapley value is inherently doing, right, is you're basically querying your model with various input configurations, and you're seeing how much your model varies, right? So what I'm actually going to very concretely do, and let me scroll back up to the relevant slide. So what you're going to basically say is, look, f of x would be the prediction on the observed point. F of x sub s will be use the S points, S features that I've selected as observed, and then set the rest to some baseline value or some reference value. And there's lots of ways to select that. And huge literature I'm happy to point you to if you're interested in that. But what happens if I query the model with this half baseline reference and half selected reference? And then if to that feature, if I add the ith feature, the one I care about, the one I want to add value to, how much does my predicted probability change? And then you weight it by some permutation term that normalizes everything. And then you do this. So this has a lot of number of queries, right? This is for what really matters here, I think, Vedant, is the size of D, right? So the number of features you matter is really what is a computational bottleneck. And then there's interesting questions on when you're calculating this kind of expectation. When you rewrite it, you can rewrite it as an expectation. Do you calculate it using the marginal or the conditional distribution, which is an interesting question that Lizzie Kumar from Utah, now Brown, has been answering. So that's quite nice. So Lime can also be applied out of box to deep learning models as well. Again, there's two questions there. One is, what is the perturbation region where you're going to fit your locally linear model? And then you're just fitting a tangent line. So you can pick whatever local model you want. So there are a lot of hyperparameters to pick, and then I think that might make practitioners a little uncomfortable generally. Yeah, so that's kind of how I answer that question. Okay. Shapley values hinder correlated features. That's a good question. So as you can see in this configuration, like, we're only considering a single feature at a time, which means that I haven't explicitly kind of studied what happens when you have interactions. So while I haven't studied this, there are people that are studying this. There's some good work coming out of UW from Sue and Lee's lab. Pascal Strumfels and Joe Jakizik have been studying this problem of feature interactions, particularly in the radiology context. So I recommend you look at their work, but they're working on taking the Shapley value and like the Shapley value explanations and kind of making them handle correlated features, or at least considering sets of features. But you can imagine there's an exponential explosion if I make this difference. If I make this difference now consider ij instead of just I alone. So you get like, it becomes a combinatorial problem and it becomes way too difficult to solve. But I don't think that really matters for the most part. I don't think that is not, I mean, these could be important in certain domains, but people are still deploying them even with these problems. So I hope that answers your question, Pascal J. Can I write the names? Yes. Sue and Lee is like the person to look up. Her lab is great. Good fan of her work. Cool. Yeah, any other questions?
I actually had a couple of questions.
Yeah.
This was excellent. Where does explanation or these explanatory techniques fit into the model life cycle of a company? I mean, is it typically a process which is done post the model is ready for deployment and now you got to vet it out because you have all these like obligations from a regulator perspective or internal policies, or is it a part of the actual model development cycle?
Yeah.
And then also budget, right? So, in terms of budget, not just in the context of computing, but also in the context of for-profit enterprise trying to like get the products out. And then there are a lot of open questions in here. And then there are a lot of what you call hypothetical questions too, right? So what if this happens? What if this happens kind of thing, right? So what kind of pragmatic things should we be looking at? That's like a generic question and I have a specific question.
Yeah, great question. So I think the big thing to consider is so let me answer your first question first. Where does explainability kind of live in the life cycle of a model? So the first step is explainability can actually help before the model is even developed. So there's been work, again, out of Sue and Lee's lab. They've tried to take a priori knowledge that domain experts have in radiology, for example, and then even work with startups for this. I have this a priori knowledge. Can I embed that into the learning procedure? So it starts way before. You have domain knowledge that you want to incorporate into the learning procedure. Explanations may help you do that. I'm just communicating it as it is. Another place where explanations are probably most used is at the phase where developers like debugging a system. So if you have pictures of huskies, and you're trying to build a husky wolf classifier, this is the classic example used in the Lime paper. You want to be able to discriminate between a husky and a wolf. You don't want to fit to the snow that is in the background of the husky. right? That ends up happening. You have these spurious correlations that might appear. You might need to be able to look at those and kind of look at them as a developer, such that when you're developing your model before production, you actually consider these use explanations to kind of run through these spurious considerations. The other thing that it could be useful for is actually providing a justification to an end user, right? This is after the models hit production. It can help you understand, well, how does my model actually behave, and what kind of information can I communicate back to end users? And we're quickly realizing that explanations might not be the best thing to communicate, right? If you have a machine learning system that predicted if someone has cancer or not, if the person, in both cases, or in any of those cases, are you really going to want an explanation in one of the forms we just discussed? Do you want sample importance? Do you want feature importance? Probably not, right? In the case of a positive classification, you are thinking about your family and thinking about the ramifications of a positive classification, right? And in the negative case, when I say you don't have it, I want you to be sure. I want to know how sure you are that I don't have it, right? So in both of these cases, an explanation is required, but not in the form that we're currently thinking about it, right? The forms of transparency that we're currently thinking about are very different, but this is after production, right? This is in the ecosystem where you're deploying the model, what happens, right? Adding a button like, why am I seeing this, to Facebook is an interesting step, but the question is, are you really getting an explanation of your model or just providing some piece of information as a form of transparency? Right? If you're just telling me that, oh, I'm seeing this ad because I'm over 18 years old, well, was that even fed into your model, or is that just an artifact of who I am as an individual, right? As the data you have on me. So it's just not clear sometimes on how faithful an explanation needs to be, what type of transparency to provide. So this is actually something we're actively studying. And unfortunately, I know while people are actually trying to deploy these systems in real time, they'd like answers really quickly. And unfortunately, like we're trying to study as fast as we can these ideas of, well, what types of transparency mechanisms correspond to what people need in various situations. Right? Do you even need an explanation? Do you need documentation? Right? If you're an auditor, do you need just documentation? Do you need to understand? Do you just need the code? Right? Can we run like verification style tests on the program to just understand how it works? Or is there some more nuanced study that needs to happen, like a clinical trial or trialing basis? So that's kind of what I would say on that front. And I guess I hope that answers your question for now.
Yeah, absolutely. The other question is, there's a plethora of research happening, and every year, it just keeps on going broader and broader. And then also in the machine learning development community, the models are getting more and more complex. AutoML,
of course,
billions of parameters in models.
Yeah.
And I don't even know like how you can explain, like a GPT model kind of a thing. So many. I mean, even industry models with millions of data points can get really, really complex.
Yeah.
Now, where is human level explanation in this whole picture? Because it becomes. I mean, I'm thinking pragmatically, like when I work in the industry, most of these people, they don't have like PhDs from the University of Cambridge to go in and like look at all these formal things, right? So they are probably coming from an operational perspective. They know how to look at accounting statements. They know how to kind of, look at like transaction records or customer records, and they don't have that ability to even express what they are looking for. So where does human level explanation fit into the spectrum, and what needs to happen to make this more accessible?
Yeah. So this comes down to that massive question that's kind of likely will be the crux of my PhD. So all this work is great, but only some of it may make it in. What I'm very interested in studying is exactly what you just said, right? Which is what is the form of interaction that an individual who may have varying levels of expertise, what kind of interaction tools can we provide them with such that they can make these updates to their model, right? So I have a machine learning system, and by and large, we're going to assume that most of these people understand that stuff goes in, stuff comes out, and I'm just very happy with the stuff that comes out, right? But I need to know sometimes, is the logic or the reasoning that's used inside similar to what I would have used if I hadn't automated it with these like large scale models. And it's just not clear that we have the tools to do that, right? So it is just so easy right now to use some of these tools, right? Use these explainability methods like SHAP and LIME kind of just provide, like, plug in the stuff that's online and kind of get explanations. But when you get those explanations, it might not be sufficient, or you don't necessarily know what to do with them, right? And how do you figure out what to do with them is a big question that's kind of at play right now. So yeah, unfortunately, I wish I had an affirmative answer for you, but I'm not yet. But stay tuned.
Hopefully we'll get there. Hopefully we'll get there. At least I hope that perspective is maintained in the research community also, that it's not only being rigorous and formal, it also needs to be accessible.
Yeah, exactly. Yeah, definitely.
So, yeah, perfect. So I know we are running a little bit late, but I'd love to kind of pick up the discussion on the second thread.
Yeah. So feel free to keep putting your answers in the Q&A, and we can take it from there. So let me jump into the second half, right? So the second half of today, I want to talk about uncertainty as a form of transparency, right? And so one of the things that we found is that that explanations itself are a really nice form of transparency, right? And unfortunately, there just hasn't been adoption. So even though we can all in our heads kind of picture like getting explanations and this like really beautiful human AI interaction framework powered by explanations, it's not clear that they actually meet the needs of individuals. One thing that they might want instead is uncertainty, right? And then what we argue in our most recent paper is called Uncertainty as a Form of Transparency is exactly this. So that'll be the crux of what I talk about here today. So the part 2 outline is, first we're going to go over existing approaches to explainability, interpretability, and explainability one more time. These slides are from one of my co-authors as well. So unfortunately, his use of interpretability is also there, but we are talking about interpretability in the context that I talked to Sri about it earlier. Counterfactual interpretability is what we'll cover, uncertainty in ML, and then we'll talk about the clue method that I discussed, and then there'll be time for questions and feedback in both parts. So largely in interpretable data decision-making, like we don't necessarily just have access to explanations, right? You might use something like a generalized linear model, which basically provides individual weights for features that you observe, and the importance is the magnitude of that weight, and then we can actually see if there's positive or negative correlations. So the sign of the weight will actually tell us what type of relationship our output has with a given input. So generalized linear models, maybe they'll correspond to a downstream explanation, but by and large, like they're largely interpretable because you know that there's individual weights ascribed to each of the input features. Then you have these idea of decision trees that some of you might be familiar with. So decision trees are inherently interpretable insofar as you can follow the reasoning, assuming the number of features used at every node is not very large, and you've learned like decision thresholds at each of these nodes. You might consider this to be interpretable, right? So if I wanted to figure out if I should go to a restaurant, the first question might be, am I hungry? And do I have $25? And if I do, then yeah, maybe you should go to the restaurant, right? But it's a very simple, like logical reasoning kind of question that you can ask. So these are interpretable ways to think about decision-making. Now, you might have these, on the other hand, we do have other methods that are like just not interpretable at all, right? You have data-driven decision-making systems like self-driving cars that use large-scale LiDAR and segmentation maps to then figure out, can we put it in autopilot or not? So these methods, these large-scale deep learning systems capture really non-linear functions, right? Neural nets, for those who are familiar, are universal function approximators, so they should be able to learn any function. And this scales to like high dimensional problems where you have lots of different data streams and multimodal systems and large data sets, and they can simulate complex systems, and they're really exciting, but unfortunately they're not very interpretable, right? So that's why we've been trying to get explanations out of them to really figure out what the heck is going on inside. Now, on the feature importance side, as we talked about Lime, just to answer Vedant's question from earlier, like again, we can approximate that function, that neural net, with that kind of generalized linear model locally. Right. So if I have this decision boundary in list shown in black, you can approximate it at the star with a generalized linear model, so a line. And the explanation has varying amounts of reliability in various areas. So it is more reliable. The explanation here shows that the model is more reliant on X1 than it is on X0. Right, that's the first thing you take away. And then you can see that will this explanation that you have at the start actually work on other data points, and that's where that uncertainty quantification that we talked about kind of comes into play. But this is just to say a nice way of saying that, look, feature importance like Lime kind of exists to take these large scale function approximators and make them interpretable in some way, shape, or form. And then because there's an interpretation, you can actually provide what we call like a Lime explanation, which is just the weights itself. Again, this can also be applied to images, like MNIST images. You might be able to get explanations for class-specific settings. And then what you can do is get like positive or negative contributions here being in red, in red, and then negative contributions here being in blue. You can use this to then think about what portions of an image are helping contribute to a particular outcome. But unfortunately, they tend to become quite meaningless for strongly nonlinear functions. And that kind of is an insight that a lot of people have kind of found over the last couple of years. So that's why you have these ideas of like DASP, deep SHAP, and different variants of kernel SHAP that kind of come into play, like these kinds of methods that people are developing that are kind of all beating away at this problem of explanations kind of being meaningless from these strongly nonlinear high dimensional functions. So one of the things that you can do instead is actually think about this idea of counterfactual explanations, right? So counterfactual explanations, just to recap what we talked about earlier, they can ask some kinds of questions of the following form. What features would you need to add or remove to my model such that my model's confidence will decrease? Or what features would I need to add or remove such that my prediction changes, right? If I can ask these kinds of questions, then I can, and ask them in a model agnostic fashion, then I can potentially provide insights into my model's behavior. So there's one group at the University of Toronto, David Duvenel's group, that had studied counterfactual explanations for image classification, right? So if you look at the input on the left, on the top left, you have this really nice bird, high probability of this being a bird. But if I do some sort of counterfactual simulation, I can actually decrease the predicted probability of this being a bird. The question is, how do you do that, right? If I had not observed this section and I'd observed this counterfactual infilling instead, right, as seen here, then my probability of it being a bird would decrease. It's quite a nice little method that they developed. And then they can show that this kind of generalizes to large scale linear classifiers. But the crux to understand here is that when it comes to image classification and counterfactual explanations, the idea of asking these questions that say, what would I need to change about an input to change my output, is equivalent to saying, which patch of image do I need to cover or basically augment such that my prediction decreases? And they do this using masks. So uncertainty in ML, kind of switching gears for 1 second, is really important, right? So you can imagine a situation where people are saying AI is going to take over the world, but in actuality, you have a deep neural network that basically classifies this cat over here as a dog with high probability, high confidence. So uncertainty actually gives us a sobering perspective on the ability of these deep learning systems, okay? And this led us to write this review paper in response to our in response to some of our work with the Partnership on AI earlier, called Uncertainty as a Form of Transparency, Measuring, Communicating, and Using Uncertainty. It was written with a bunch of folks at Intel and at CMU, Element AI, Turing, Sony, and NYU and lots of different places. So it was really mammoth effort from lots of people, but it's important. We think it's really important work because it helps us kind of think about how we can think about uncertainty as a way to be transparent. Right? So let's first start talking about uncertainty and let's dive into that first. So as I mentioned earlier in the talk, algorithmic transparency is this umbrella term where we've kind of been focusing on explainability for a while, but uncertainty is another form of transparency, right? I'm looking at explainability as a popular form, but can we actually move beyond this, right? What other forms of transparency can I provide about my system such that I can build like better human AI teams and so on and so forth? So many communities have actually decided to study uncertainty, but what we really wanted to do with this piece is aggregate the salient points into one coherent piece for people to reference. So let's jump right into it. How do you quantify uncertainty? So you might have heard of uncertainty. No, the simplest thing to think about is if you have a machine learning system that outputs predicted probabilities, in some way, shape, or form, you're actually outputting uncertainty, right? So if I'm 99%, if it's 99% probable that I'm in class 1, then that is one way of saying that I have that I'm quite certain. And 90% probable that it's class 1. It's like, I'm not as certain as the 99% guy. Okay. And what we can do is actually measure like the predictive entropy over that probability distribution and treat that to be a form of uncertainty. Okay. And I'm going to walk everybody through this really slowly because I think it's really important to know. And then it's similarly with regression problems as well. But I won't jump into that. And again, going back to what we were talking about earlier, you might be able to obtain uncertainty estimates by just ensembling different elements from different models into one model fit to the same exact data and taking the average of their predicted probabilities or the variance of their predicted probabilities as a form of uncertainty. And that breaks down into two different forms of uncertainty. One's called aleatoric and one's called epistemic. That's a preview of what I'm actually about to jump into. But the thing to take away is that predicted probabilities are actually a form of uncertainty in and of itself. And there are various uncertainty measures that we can put on top of this kind of distribution such that we can measure uncertainty. So what even is uncertainty? Like what are the sources of uncertainty? So if you look on the left-hand side here, right, on the bottom left, you'll see this classic Moons data set. Classic Moons data set, what we've done is we've fit a Bayesian logistic linear regression to this data set. And what we found is that it helps us, what we can do is we can actually decompose from the posterior of our weights given our data, we can actually decompose our uncertainty into two components. The first is shown in the center. It is called noise uncertainty, also known as aleatoric uncertainty, which appears in areas of high class overlap, right? So in the center of these moons, it's not necessarily clear if I'm fitting just a line what class is which, right? Because a line alone, recall linear regression implies that we're fitting a linear hyperplane in R2 to this data. How are you supposed to know what happens around that decision boundary? There's so much class overlap that we have aleatoric uncertainty in the center, right? Which is what kind of appears right around that area of high class overlap. And the other form of uncertainty, which is classically what people associate with uncertainty, is known as model uncertainty, which answers the question, or also known as epistemic uncertainty, which answers the question, have we observed enough data to make confident predictions, right? If we don't have enough data, then we might not be able to make confident predictions and might have our probability distributions kind of be all skewed. So as you can see, as you grow further away from the data set, the right-hand side denotes the epistemic uncertainty. So white being high uncertainty and black being low uncertainty. The epistemic uncertainty decreases as we move away from the observed data. People classically say that with aleatoric uncertainty, you can decrease it by acquiring additional features. And epistemic uncertainty can be decreased by acquiring additional data, right? So what you want is you want to observe data in these really white corners to really understand like how to decrease epistemic. And you want additional discrimination in the features along that white line in the center figure to decrease aleatoric uncertainty. These are the two forms of uncertainty: class overlap, aleatoric; insufficient of data, epistemic. There are other forms as well, and I'm happy to jump into those as well. But these allow us to we can decompose the uncertainty in probabilistic models using this kind of framework. So what is model uncertainty? Because I think that's probably a good place to start. So I'm going to assume that everybody here is familiar with Bayes' rule. What we have when we think about Bayes' rule is we might have a prior for a biased coin, and a prior is the predicted probability of a particular weight configuration, right? A particular set of a particular line, and the other thing we have is a likelihood, as you guys can see. A likelihood is what is the likelihood of us observing the data that we have given the model that we've selected, and what this allows us to do is it gives us what we call posterior, which is what is the probability of having weights of us observing the said weights given data, right? So in short, when you're thinking about Bayesian machine learning and probabilistic models in general, what you really want is a really nice posterior, predictive posterior, but a posterior of your weights given your data. Because at the end of the day, I'm given a parameter space and I'm given a bunch of data points, and I'm saying fit the model to fit me a model to the data that I've observed. And the way Bayesian machine learning people do it is actually assuming a distribution over all possible models. And there's two components to that. One would be having a prior, right, on like what we think the weights should be, right? Was it a line with positive slope, negative slope, whatever it might be. And then the likelihood, and how likely is the data that we've observed under the model that we found. I'm not going to jump into the coin tossing experiment because I want to get to the questions at the end. So when it comes to understanding model uncertainty, you have lots of different weight configurations that we might obtain if we use like simple gradient descent, right? So you might end up in the local minima that's the red star, or the blue star, or the green star, right? It's a non-convex optimization landscape. What Bayesian machine learning allows you to do is consider a bunch of models, right? All the red model, the blue model, and the green model all at the same time, such that you can take the data that you observe on the left, get a bunch of models as you observe in the middle, and then assume basically predictive error bars and mean bars across the entire distribution of models you observe, right? So this is sampling on the last slide from probability of W given the data. Okay, so given this, you can actually then say, well, model uncertainty allows us to go from single weights, right, vanilla DNN that you might train in TensorFlow, to probability distributions. So instead, we assume that we have probability distributions for weights. And that's quite nice. So that's like a 101 on probabilistic models. So one of the things to note is that, look, when we're fitting these models, we usually use these posteriors and we use approximate distributions instead of the actual non-convex landscape, right? So non-convex realistic loss landscape is what you observe on the right. But in actuality, we're going to approximate it with some really nice distribution that we know. So just noting that our uncertainty estimates are going to be biased by our approximations, but that's not necessarily worth thinking about at the moment. But that is something to keep in mind. So how do you then quantify uncertainty, right? So in classification settings, we look at our predicted probability distribution and we measure how much entropy is contained inside that distribution, right? So if I don't know what class it should be, then I have high entropy in my predicted probability distribution, right? So I'm quite uncertain if I give equal probability to all classes. But if I give high probability to one class, then that means that I have low entropy. Okay? And then in the regression setting, we look at the predictive variance. So how much across all of our models does our output for a given point kind of vary, right? And that kind of gives us these large error bars that you'll observe. So recall that the data points that you have found are the ones that are in black, but the predictive variance is kind of what exists in between the data, or outside the regimes where data exists. Okay, just before we do that, just going back for this last example, I'm going to go back to the beginning really fast. Sorry. So if you look on the left here on the right side figure and the leftmost thing where it says ensemble element predictions, you'll see that each of these blue lines corresponds to a different model sampled from our posterior distribution of weights given our data, right? And our internal noise model, which is incorporated into our probabilistic model, gives us the red, this kind of orange line, which tells us the aleatoric uncertainty, right? And when combined together, you actually get the predictive uncertainty, which is a combination of epistemic and aleatoric uncertainty, right? So there's a really good review that I think I included on the breakdown between aleatoric and epistemic that I highly recommend looking at. I think that could be quite nice for those that are interested. So how do you actually use uncertainty in practice? So when it comes to fairness goals, you might consider using uncertainty to look at measurement bias or sampling bias. So measurement bias might be the idea of having noisy features or noisy sensitive attributes. Remember, a noisy sensitive attribute is actually equivalent to having aleatoric uncertainty, right? And sampling bias is basically when we oversample in a particular region such that we have an unfair model because we've oversampled, let's say, in one portion of the world and then don't really have a representative sample. That is a form of epistemic uncertainty. There's a cool paper from Krishna Gumadi's lab that kind of studies this a little bit more carefully, that was published concurrently to ours. With respect to decision making, we might be able to build what we call rejection option classifiers. These classifiers kind of will reject doing prediction when the entropy of the predictive probability distribution is very high, right? So if the predictive posterior has a high entropy, that implies that all of my models disagree, which means that I might want to reject doing prediction and then defer back to a human instead. And when it comes to trust formation, uncertainty can actually be seen as displaying the ability of the model, right? By saying that here's what I know, here's what I don't know, because that's what uncertainty kind of tells us. Benevolence, which is a form of saying that by communicating uncertainty, you're actually displaying benevolence by showing that you are in good faith communicating when your model knows what it knows and knows what it doesn't know. And integrity is actually saying that my uncertainty actually comes, my uncertainty actually leads to, my uncertainty actually implies that I actually am uncertain about this model, right? So, yeah, that's something that that I'm actually uncertain about a particular data point. Yeah. So these are the ways you can actually use uncertainty in practice. So other ways uncertainty can actually be used in practice is actually thinking about like these robustness applications. Again, back to reject option. When you're doing medical diagnoses, if you've never seen a particular patient before, you might actually want to not provide a prediction in that setting, right? It's another form of transparency because I'm actually telling you that my model doesn't know anything. Therefore, I need to give users a seat at the car instead, right? When you're building data sets and thinking about fairness, you might want to identify, like, again, disparities in representation between subgroups. And also when you're thinking about different data sets, like you can use uncertainty to actually think about active learning strategies to acquire additional data. And that has made very large strides in like molecular design and drug discovery as well. So if you want to try out any of these Bayesian deep learning things I've been talking about, there's a link to a GitHub repository in the slides from one of my close collaborators here at Cambridge, Javier, these are actually his slides, just the last few slides. So when it comes to communicating uncertainty, one of the things that we find is that once you've quantified it, right, and once you've measured it, it's really important to actually tell people that you've measured it. One of the things that blew my mind when I started working on this was how can uncertainty be communicated to stakeholders as a whole, right? And as a kid, I used to see this on the screen all the time when you see hurricane forecasts. But it's not that the hurricane actually gets bigger, right? This is a hurricane forecast that you're looking at. It's that we actually become so uncertain about where the hurricane is going to go that we provide a very large band. There's actually a variance band for where the hurricane's true trajectory is going to be, right? So uncertainty is actually being communicated all over the place, but really understanding that end-to-end workflow from quantifying it to using it to then communicating it is quite important. So for example, you might communicate it as a fan plot, right? Basically showing that I have estimates for the number of crimes that people are going to commit, but actually I get quite uncertain over what I'm going to observe tomorrow. This is exactly kind of why uncertainty is really important to those dealing with time series data, like stock market prediction, for example. Various ways can be, you can use various like methods to actually communicate it, right? You can actually show the predictive distribution, show error bar as well that you might be interested in looking at it.
So I think there was a little bit of microphone issue there, Umang.
Yeah, sorry. Is it better now?
It's better now. Perfect. Thank you.
Yeah. So uncertainty, how to kind of like communicate that to end users. So the real question that we have then is that are uncertainty aware systems interpretable? And the idea is that they actually are, and they're actually just as interpretable as regular models, right? And this is interpretable in the form of actually being able to see what's going on inside, maybe not communicate as an explanation. So uncertainty can actually help people understand predictions in some use cases. So there was work on polyp segmentation that basically people use uncertainty to figure out where are we uncertain about this polyp that we've classified, right? And that's actually quite useful, right? Because I'm telling you where in input space you are uncertain. And the method that they use here was actually leveraging some of the feature importance explanation methods that you'd seen earlier. But what do you do when the model doesn't know an answer? So this is a proposed workflow that we have, is that if you have an input and then a probabilistic model, If you have a certain prediction, then you might want to get an explanation from Lime, Shap, integrated gradients, or Fido, which is the method from Chang et al. That we talked about earlier. But if it's an uncertain, if you're going to reject it and have an uncertain prediction, what type of explanation do you provide? And this is kind of leads us to our other work, which appeared as an oral at iClear this past year called Getting a Clue, a method for explaining uncertainty estimates. So this appeared earlier this year at the International Conference on Learning Representations. So yeah, I'm going to jump into this now. So when it comes to explaining uncertainty estimates, we really want to highlight the evidence for each class, right? And there might be conflicting evidence in the form of noise, right, as observed with aleatoric uncertainty, or with the lack of evidence for the predefined classes, which is epistemic uncertainty, right? So recall that uncertainty estimates are nonlinear for even the simplest models. So we actually try to pose this entire problem of explaining uncertainty estimates via counterfactuals. So how can we ensure that the counterfactuals are relevant is our first question. So when we have adversarial example, like for those who are familiar, like adversarial examples basically are this idea of taking noise and adding it, a very specific type of noise, adding it to an input and actually changing the confidence and the classification of a particular output. What we actually notice is that if you actually just do normal gradient descent from a point that you observe to a point with lower uncertainty, so basically differentiating with respect to the uncertainty estimate you have, you actually obtain an adversarial example. So that's not necessarily good. So this is why we have to propose this thing of idea of clue. And we take inspiration from the data-driven drug discovery literature, where people restrict the hypothesis class to the low dimensional manifold of a generative model. So we take a deep generative model that's trained to kind of generate new outputs. So this is like a variational autoencoder or a GAN technically, or a normalizing flow really. And what if we do optimization in the latent space where we have a smooth manifold, right? And this makes sure that we have relevant proposals and not adversarial examples when we're trying to identify which features are contributing to uncertainty, right? So if we look at this example over here, back on this other slide, the adversarial example, when we just do gradient descent, says this uncertain thing that looks like an 8 can become more certain if you inputted the thing on the right. But the thing on the right is not necessarily what we want. It's just an adversarial example. It's not that helpful. So though it has low entropy, it is off manifold input. So what we actually do is we then say, let's actually do the same thing for counterfactuals and do that optimization in the latent space of a deep generative model. If we do that optimization, if we do that optimization, we find that we can get an on-manifold clue, and look, now you can actually see that this ends up looking a little bit more like an 8 because we stayed on manifold, the data manifold of MNIST digits. So our method is called CLUE, Counterfactual Latent Uncertainty Explanations. And it asks the question, what is the smallest change that you need to make to an input while staying in distribution such that our model produces more certain predictions, right? So by staying on the data manifold, this requires like the use of a deep generative model for us to basically say, can we find a input that's nearby to the input that I've observed that is on manifold that leads to lower uncertainty with my classifier, right? And then we can get a saliency map in the name of Lime and Shap that tells us where that uncertainty lies. So for example, if you see this input on the right, on the left, you have this input that's really uncertain, you feed it through a probabilistic model, and if it's a certain prediction, if it's certain, then you might use regular interpretability, but if it's uncertain, you might use CLUE. And what does CLUE say? That this little 6 that's connected can actually become certain if you remove the the blue region, right? So that little connection, that error that you have. So another way of thinking about this is if you have a classifier that's discriminating between 4s and 7s, and you train the model just on 4s that are open on top and 7s that do not have lines down the middle, then if you observe a 7 with a line down the middle, you might get an uncertain classification, but that uncertainty is not because of the 7, but actually just because of the line that you observed down the middle, right? So we know where the uncertainty might lie, and how can we explain where that uncertainty lies? So we try to bring uncertainty to the input space level. So the algorithm is actually just generating a counterfactual, doing optimization in latent space, and then kind of doing gradient descent through the whole thing. I'll leave those that are interested to the paper to kind of think more about this. So what that we can then do is we can actually then display these clues to users, right? So we can then say, look, like if you have this original 0 that is kind of unconnected, connect it, make it a little thicker, and then I'm pretty certain that it's a 0, right? Or if I have like an LSAT data set where I'm trying to predict if someone's going to do well in law school, I might tell you that you need to change these few things about this individual in order to get a more certain classification out of my machine learning system, right? And that's kind of what we say, like lower this person's GPA, change their race, and actually you can get a more certain classification, right? So this just tells you, it gives you an understanding of what the certainty landscape of the system is, not just of the loss landscape. So we can then compare it to Lyman Schaap, right? So on high dimensional, on uncertain images, Lyman Schaap don't actually perform as well, which confirms the conclusions that we had in our uncertainty explanation paper. However, what we find is that Clue, because it uses a generative model, can actually add new information. So Lyman Schaap are restricted to the data manifold, are not restricted to the data manifold because they kind of do this like weird perturbation-based stuff. Clue can actually generate new pieces of information that might not actually exist. And what that does is it allows us to take an input and apply Clue to it to see what would need to change in order to make it more certain. So we then had a user study where we showed people an uncertain example and then a certain example. And then we said, given unknown data point, right, a new data point, can you predict if the model is going to be certain or not certain on it, right? Because the whole point of Clue is to understand the uncertainty landscape of my machine learning system. And then we find that, and the way we kind of set it up is we had done it with like university students and then done a bunch of approaches, both on tabular data. I'm not going to get into the details of how we actually kind of went about the workflow of the experiment itself. But what I will say is the findings, when we actually showed people random certain points, they really struggled to identify the certainty of the unknown point. But with clues were really able to contrast the two, the uncertain points from the certain points to basically make it easier for people to find a test point that to identify the certainty of a test point, right? And it was rather quite statistically significant, our findings. And the same thing kind of happens with images when we do the same thing. So again, if you have a model that's just trained on lines down the middle, well, without lines down the middle, by removing the line down the middle, you can actually get a certain input, right? So this, and same thing with a 4, right? If you have a 4 that's closed on top, you might need to remove the top in order to become more certain, right? So again, I guess this is a long story short. What I would talk to you about today is the challenges that are associated with explainability, how uncertainty can be seen as a form of transparency. And as a whole, I'm really excited about the challenges and the frontiers that we face in making transparent machine learning a reality. So thank you for listening. I'll take questions now. Feel free to reach out on my email below or on Twitter or any social media if you're interested. Thank you for your time.
So thank you so much, Umang. This was an excellent presentation. I'm so fascinated. I should kind of go back and look at all the links you've been sharing and look at all the work, which is really, really awesome. And so I think there are a bunch of questions in here. So I'll start out with the last two, which are associated with the uncertainty ones, and then we can kind of probably revisit some of the questions we didn't get a chance to answer regarding the first part. The first question from Vedant, how can you use Gaussian processes for modeling uncertainty? Is that something you've looked at?
Oh, I guess so. Yeah, GPs inherently have uncertainty because you have so Gaussian processes, for those that are not familiar, model a distribution of functions as opposed to a distribution of like specific weight configurations. So GPs inherently have uncertainty. So it's the same idea in like the basic idea of like Bayesian machine learning. Again, look, we have a posterior, instead of having a posterior weights, we have a posterior all possible functions. And usually you have what we'd call like a GP prior that you can then use to get uncertainty estimates from other systems as well. I recommend Carl Rasmussen's textbook on this. He's a professor in our group and is really, really good on this. He wrote the textbook on it. So for those that are interested, it could be quite interesting. And I guess I see in the second question, how do you know in the case of low dimensional manifold, how do you know it is best to? Yeah, so good question. So in the paper, we talk about this. what we really want is a differentiable lower dimensional manifold. So not something like TSNE or UMAP, right? But what you want is the quality of the VAE, the size of the latent dimension are all things that affect clues. So I highly recommend, if you're interested, to go look at the paper, because we do have experiments for all of this. And obviously, I think as expected, this method will depend on how good your generative model is, because I'm basically doing latent space optimization instead of doing optimization on input space, because input space is what led me to get those adversarial examples.
Cool. And are any of the methods you presented in the uncertainty quantification toolbox? With the idea
Yeah, so everything except Clue is in there. Clue, we have our own repository that we're going to release shortly. But if you're interested, you can email me and I'll send you the code, because it's not up on GitHub yet, but it will be shortly. And we're working with the IBM team to put Clue in the toolbox as well. So it'll likely be in the toolbox, hopefully by the end of the year. And I'm interested in the importance of a particular feature from a pool of features. The models trained on classifications. What sorts of methods to use? Oh, yeah. I mean, this is like standard SHAP Lime can be used for this kind of stuff. If you have a set of features, you might want to just understand the importance of a particular feature to a model, like Shapley values in Lime are kind of like the things that you want, unless I'm misunderstanding the question. For Bhaskarjit, the question, yeah, so Lime, I guess I don't see explanations as a product itself, because it's kind of very tough to do that, because it's going to be very user specific and specific to specific instantiations. So a lot of the companies that were originally pitching themselves as explainability startups are now pitching themselves as ML ops companies, because they're going to continuous monitoring of explanations or of the machine learning systems as a whole. You're also seeing that TensorFlow and PyTorch are embedding explanations directly into it. SageMaker has made it really easy with their new Clarify tool to kind of embed explanations directly into the learning procedure. So I don't see it as a product in and of itself, but rather something that augments the things that people have already created.
Cool. So I think we get to this question, I'm interested in understanding importance of the particular feature from a pool of features on which my models are trained, the classification scheme. What sort of methods can I use to get that importance?
Yeah, so I guess I'd say the same thing, which is like Lime and SHAP probably are the ways to go. So it likely makes the most sense, assuming you have the models trained. If you don't have the models trained yet, then you can do like feature selection schemes as well.
Okay, cool. Now, regarding uncertainty quantification for machine learning models, so what classes of models have you looked at? I mean, like really deep learning models, are they some things you can look at, or do you have recommendations, ensemble models?
So for Clue, you can have an ensemble of differentiable probabilistic models and you should be good. But if you're using something else, like we likely want to think about like probabilistic models here, right? So there's this really famous paper from Google, from Balaji's team. Actually, it might have been from DeepMind when he was at DeepMind, where they basically showed that you can get really well calibrated uncertainty estimates if you use a deep ensemble, which is just multiple deep learning models trained with different initializations. I mean, you can basically get good uncertainty estimates from just training multiple times, which is pretty tough, right? That implies that you have the compute to train multiple times some of these big models. So yeah, I guess probabilistic models and ensembles are probably the way to go when thinking about this, and ensembles of differentiable models are probably the best thing. Yeah.
Cool, awesome. And do you have any thoughts on tying uncertainty to risk and the criticality of specific kinds of outcomes?
Sorry, connecting it to what?
Criticality and the risk of certain types of outcomes.
Yeah. So this is like why I think reject option classification and learning with deferral is important. So if we can use uncertainty to figure out what are the risky labels that we may predict for, then you want to make sure you are very certain before you make certain prognosis in the medical setting, or if you make certain like financial decisions in fintech. So it's really important to have well-calibrated notions. What that implies is that we need to learn those thresholds of when to defer those to humans And it's not clear on how to do that right now. So we have a line of work where we've been thinking about how do you take uncertainty methods and combine them with something called conformal methods, which provides you with set of predictions instead of a single prediction. So you can take that uncertainty from instead of just being a number, I can actually now make it just a set, which with high probability contains the true label. And then we can kind of take that from there.
Mm-hmm. Yeah. Okay. Cool. So I think we got through all the questions.
Yeah.
So this was an excellent presentation, Umang. Thank you so much for taking your time and presenting. And this was a lot of learning from me. I was kind of taking notes as we spoke. So thank you
for having me. Yeah.
And all the attendees, if you have any additional questions regarding either of the presentations Umang presented, please reach out to him directly. He's available on Twitter, LinkedIn, and you should be able to Google him up. Also, some of the links he has been posting are available on the webpage. And also, I'm just going to do one more quick thing before we adjourn for the day. We have all the presentations. So I think all the slides which Umang presented will be available on Curate Academy. So, and all the rest of the presentations which has been happening in this session, please register at Curate Academy to access those. And as I mentioned, next week, so on Curate Academy, you just go in there and you register to summer school, and you should be able to access all the presentations and the videos. And next week, as I mentioned, we have Navdeep Gill from H2O.ai, and he'll be presenting his work on machine learning security. So thank you all for joining us today, and I hope you have a wonderful rest of the week. And thanks again, Umang. Good luck with everything.
Thank you so much.
Bye.
Cheers. Bye-bye.